right? I think you're finished taking that equation off in terms of the cobalt. And by the way, the
No,
asterisk.
sir, I'm not finished.
All right, cool, cool. The asterisk beside it just means that it is unstable. You understand? It just means that it's unstable. So the general form is to say that X, which is your parent nuclei, is going to break down. When that breaks down, it doesn't change. So it's the same element, having the same mass number, having the same proton number, but you just want to know and say, yeah, uh, gamma ray is given off, which doesn't have any mass and is not charged. So this is like the equation that covers that, so to speak. Oh, go on, yes, I know. Now, remember in previous lesson, or even within the same lesson, we talked about the deflection of the alpha, beta, and gamma, right? In an electric field and in a magnetic field. This is what it looks like for the deflection whenever you're pretty much detecting rather, you know, these alpha, beta, and gamma particles, right? So if you have a parallel plate that is set up right here, cool. What you would expect, because beta is negatively charged, as I would have stated some time ago, right? Then you would find that the beta particles would move towards the positive plate. Now, because alpha, which is positively charged, right, which is a helium element or helium nuclei, that in itself is going to move towards the negative plate because we know that positives and negatives attract. Because gamma, right, which does not have any charge, this is the reason why it passes through undeflected. Now, this is for the electric field. For the magnetic field, deflections occur, right, based on the fact that alpha particle is positively charged. So by using Fleming's left hand rule, you would realize that the alpha particle would move upwards, providing that the magnetic field is going into the paper. So once the magnetic field is going into the paper, then you expect that it's going to deflect up like this. Cool? As in regards to the beta particle is opposite to the alpha. So whatsoever is happening to the alpha going up, then beta particle is going down. Mind you, the lines are a little bit longer. So alpha has a much what would I say now? It's slightly deflected. It's slightly turning, but with the beta now, it's more of a rapid turn. If you check it out, you have a more curvish thing going on right here. For the gamma, of course, because it doesn't have any charge, it passes through undeflected. Now, there are certain experiments that we can use whenever we want to identify the type of radiation that is being emitted. Good. Now, a typical example here is outlined right here that you could possibly use. It says due to their different penetrating power. So different particles, different radiation have different penetrating power, right? And it says that these types of radiation emitted from a source can be easily detected by using this particular device, which is what we call a Geiger-Müller tube. But it does not only work with that. You have to use what we call a counter. Now, the counter is the device that is going to count the amount of alpha or beta or gamma particles that it is detecting. Now, in order for us to do this, right, we must be able to can find the background count, which is what we call the background radiation, right, before starting the experiment, as you can imagine, because there's radiation all around us, so it's important that we find the background radiation in the process. So step two, so this is basically talking about the experiment in a sense. So step two is for us to place the alpha, not the alpha, but the source of the radiation close to the Geiger tube and measure the count rate, right? Which is quite easy. I'm going to show you the diagram very soon. Um, then it says place a sheet of paper between the source and the Geiger tube, right? And measure the count rate again. If the count rate decreases significantly, then the source is emitting an alpha radiation. So once you see that the source, the count rate is decreasing, then that just shows up. You say, all right, paper is blocking alpha particles, and hence why it is decreasing the count rate. So you will repeat the experiment, right, using different materials such as um, aluminum foil, because we know aluminum foil is used to block beta particles, cool, and also by using several inches of lead, right? If we see that the count rate is decreasing significantly, then that just speaks to the fact that alpha, beta, and gamma particles are coming from that source, right? Because one source can give off several different type of radiation, right? So that's what is really taking place there. Now, as it pertains to other detectors, because we that's just an experiment that we're talking about there, right? How you would use the Geiger-Müller tube. It is the more recommended one because of the fact that it allows us to identify all three particles at once. You understand? But there are other means of detecting radiation, such as what we call a photographic film, right? So this can detect both alpha, beta, and gamma particles, yes, but it does not give us accurate measurements, or it does not tell us exactly if this is alpha, beta, or gamma. Um, there's what we call a spark counter. This is just only able to detect alpha particles. What we call an ionizing chamber, right? This is mainly used to detect alpha particles again because alpha particles has very high ionization abilities. A cloud chamber on the other end can detect both alpha and beta particles, and this is really due to the whole ionization ability, just the same as it pertains to the Geiger-Müller tube now. This now is easily able to detect all three of the radiations, right? So here are some information as to how the photographic film or the photographic plate rather works. It says scientists working with radiation are equipped to wear, right, a sealed badge containing a photographic film as a personal radiation monitor. It says that the film is placed and developed rather at regular at regular intervals of time, and the amount of blackening on the film indicates the level of exposure. If the level is too high, the worker must be checked by a doctor, and the area they work to in checked for leakage of radiation. It says that there is a limit as to how much radiation a worker can be safely received during a year. All right, so the spark counter now. This one is somewhat more technical in itself. It says that when nuclear radiation passes through the gap between a positively charged plate grid and a negatively charged metal plate, it says ionization occurs. It says that the ions and the electrons produced enables a large current to suddenly pass through the air under the high voltage between the grid and the plate. It says that it produces sparks in the presence of an ionized particle, right? So what you're essentially seeing is when that alpha source is shone or is emitted, or emits alpha source over this particular grid right here, which is positively charged, right, and the bottom plate, which is negatively charged, right? what you would see is that there's some type of gas that is inside, and when that alpha particle passes through it, it's going to ionize the particles. When it ionizes the particles, you have both positive and negative charge moving around, which can in turn um, create a spark. So whenever that spark occurs, then it just goes to tell us that alpha particle is really present, because alpha particle is the one that really um, produce high ionization. You follow me? So whenever that happens, you expect a spark due to the fact that um, you have positive ions and electrons, which would essentially produce a very large current. You understand? Because positives and negative attract, and so it says here that it would produce a spark. So I wonder what a spark look like. So like when something gashes, that's what we mean, right? For the cloud chamber, it says that this is just kind of explaining what happens inside of the cloud chamber, right? So it says that a felt slit round the edge top of the chamber is soaked with alcohol. I will show you the diagram. It says that solid carbon dioxide cools the chamber at a low temperature. It says that the alcohol vapor condenses on the iron caused by the passage of the alpha particles. It says that jet trail is left behind. This is what it looks like. So there's one section here that some amount of alcohol is placed at, right? So this alcohol is obviously some type of gas, right? It's going to give off a little bit of gas in a sense, some fumes. Now, solid carbon dioxide is here, which is going to lower the temperature inside of the chamber. So this alcohol gas is going to condense, and by condensing now, right, whenever the source is emitted inside, right, it will in turn cause the it will cause some type of ionization, right, between the condensed um, vapor, right, from the alcohol, right, thus causing a cloud-looking kind of thing occurring inside of that whole chamber, right? So whenever you see different shapes of lines, part, when you look at the cloud chamber, right, then that just sort of just show you whether this is an alpha particle or beta particle or gamma particle in a sense, right? So if you check this, this is a very important diagram for us, because you must know whenever you're using the cloud chamber to identify alpha particles. So if you're seeing some very straight lines, then that speaks to alpha, right? If you're seeing twisted tracks, right, then that just show that that is an that's a beta particle, which is an electron. It says that they are small in mass, and so they bounce off the air molecules and collide. So this just show how it moves, because it's going to obviously collide with the air molecules or the condensed alcohol, right? And so what you see now is that some of these electrons are going to collide and then now twist up themselves in a sense, as it pertains to the alpha again now. So alpha, because it's very heavy, it's going to just give one direct hit and then it stops, right? Some is going to pass through, so that's how far it goes and all of that. As it pertains to gamma now, as you can see, the cloud chamber can detect it in a sense, but you have to be very keen to the eye. You have to be looking for it, right? So it's going to be very tiny movements here, just showing us what essentially is taking place for the beta particle. Cool. So it says that there are scattered thin tracks whenever you're trying to identify the gamma particle. This is just another example. You can read the information. All right. As it pertains to the Geiger-Müller tube, how it works now, because this is something that we ought to be able to speak about how it works, right? So let's look at it here. We must be able to describe it and see what it looks like. So this is the diagram of what the Geiger-Muller tube looks like. And as the name suggests, Geiger-Muller tube, it was named after the persons who first, were able to measure that radiation, background radiation, and all those crazy things. So this is what happens in. So it says a thin mica window, right, at one end allows nuclear radiation to enter the tube. It says that the tube is filled with argon gas, argon gas at low pressure, right? And it says that a high voltage power supply maintains a very large potential difference between a thin window that runs along the axis of the tube and the tube wall. It says that when the nuclear radiation enters the Geiger tube, argon, or I don't know how to pronounce that word, ions, or atoms rather, are ionized. You follow me? So there's some amount of gas that is inside of this thing right here. So we have the argon gas. And when that alpha particle or whatsoever radiation enters it, right, it's going to cause the thing to ionize. And when that ionize now, because of the fact that you have a potential difference attached to this end and to the metal in between the argon gas, then those ionized particles, right, is going to attract themselves to that positively charged area, thus creating a very large potential difference. You understand? And you could now use what we call the counter. So once you detect or once you pick up that, there's some signal in the wires by nature of the electrons attracting to the positive, then it's going to allow current to flow through the to the counter. So that's how you're now able to detect whether some particle is present, yes or no, because of the fact that each time an electron is released, right, it's going to draw itself closer to the positively charged metal, thus giving a signal on the counter. So you can't use the Geiger-Muller tube without a counter. So as I said, the counter is just the device now that tells us how many times am I detecting that something is inside of the tube. You follow me? Yeah. So this is just what it looks like from another standpoint, right? Be able to can label the thing. So this is the mica window, thin mica window. So that window it's pretty much like a thin piece of material that does not allow the argon gas to escape, right? And if you see something as a rate meter, right, it's also another device that you can pretty much use to measure how fast that particle is entering or colliding against with the metal here. This is what it looks like in the lab setup mainly, right? That's what it looks like. This is the counter. Cool. This is that when ionization radiation enters the Geiger-Muller tube or the GM tube, it says ionized ions and free electrons are formed. It says a flow of charge takes place and causes a pulse current. The pulse current, right, is amplified and counted electronically, right? Now here are some questions that I have found pertaining to just what we have been looking at overall. And I want you to go through them. These are possible questions, right? So I want you to answer these, plot the graph, of course, try to solve the questions, find the decay constant of technetium, find the half-life of technetium. So you're using the graph to do mainly most of these things, mainly, right? Here's another question. Don't do this one, right? But I just wanted to show you that, as a matter of fact, I think we made mention of the experiment already pertaining to this, right? With the Geiger-Muller tube. So this is the source, and you have it placed at some distance away from the Geiger-Muller tube. Now, depending on what you detect, or from the distance, then that will tell you, whether it probably might be an alpha particle, beta particle, or even gamma, because you know the range that an alpha particle can travel to, you know the range that beta particle can travel to. So by varying the distance, you can see whether or not this source is actually a beta, gamma, and all of that kind of niceness. All right. Here's another question, totally different question that speaks to a radioactive material that is being monitored over 12 hours, right? So as you can see, that particle is disintegrating over time, right? So they want us now to plot a graph, right? So have to know that this is going to obviously be a curve when you're drawing it. Then they asked us to explain how would you determine the background count. We talked about this already in terms of background count. Let's answer those questions for practice, right? See how best you can answer this last one as well. And that pretty much explains it, all right?